In the mythology of ancient Greece, Uranus was the primordial god of the sky itself, the starry heavens personified, while Neptune ruled the vast and mysterious oceans of the Roman world. Today, these names belong to two distant worlds that drift through the darkness at the edge of our planetary family. They are the ice giants, the forgotten siblings, the mysterious blue wanderers that most people rarely think about. Tonight, we journey to these remote realms together. We will explore their discovery, their nature, their moons, and their secrets. The night of March 13th, 1781 was cold and clear in the city of Bath, England. The winter air carried that particular stillness that astronomers cherish when the atmosphere settles into calm layers and the stars burn steady and bright against the velvet darkness. In a modest garden behind a townhouse on New King Street, a man named William Herschel was doing what he did nearly every clear night. He was searching the heavens. Herschel was not, by profession, an astronomer. He was a musician, a composer and performer who had emigrated from Hanover in Germany some years before. He played the oboe and the violin, conducted orchestras, and gave music lessons to the children of wealthy families. But his true passion lay elsewhere. In the quiet hours after concerts and lessons, when most people surrendered to sleep, Herschel turned his attention to the sky. He had built his own telescope, grinding and polishing the mirrors himself with a patience and precision that bordered on obsession. His sister Caroline assisted him in this work, and together they had created an instrument of remarkable quality. The telescope that Herschel used that March night had a mirror just over 6 inches across, modest by later standards, but excellent for its time. Through this carefully crafted eye, Herschel surveyed the stars methodically, mapping their positions, noting their brightness, searching for anything unusual. On this particular evening, Herschel was examining stars in the constellation of Gemini, the twins. He moved his telescope slowly across the field of view, observing each point of light in turn, when something caught his attention. There was an object that did not look quite right. Most stars appeared as perfect points of light, sharp and unwavering. But this object seemed slightly different. It had a visible disk, a tiny but perceptible roundness that stars simply do not possess. Herschel's first thought was that he had found a comet. Comets were exciting discoveries, and finding one could bring recognition and prestige. He noted the object's position carefully and returned to observe it over the following nights. What he saw puzzled him. The object was moving, which was consistent with a comet, but it was moving slowly, much more slowly than most comets. And it showed no tail, no fuzzy coma of evaporating gases that typically surrounds a comet as it approaches the sun. Herschel reported his discovery to the Royal Society, describing it as a comet. But as weeks turned to months, and astronomers across Europe trained their telescopes on this mysterious object, a remarkable truth began to emerge. The object's orbit was not the elongated ellipse typical of comets. Instead, it traced a nearly circular path around the Sun, far beyond the orbit of Saturn. This was not a comet at all. William Herschel, the musician from Hanover, had discovered a new planet. The significance of this discovery is difficult to overstate. For thousands of years, humanity had known of only 6 planets, including Earth. Mercury, Venus, Mars, Jupiter, and Saturn were visible to the naked eye, and had been known since antiquity. They were named for gods and woven into mythology, astrology, and the very fabric of how humans understood the cosmos. The idea that there might be another planet hidden in the darkness beyond Saturn had occurred to very few people. The solar system, as far as most were concerned, ended at Saturn's distant orbit. Herschel's discovery shattered this ancient assumption. Suddenly, the solar system was larger than anyone had imagined. If one planet could hide in the darkness, might there be others? The discovery opened a door in the human mind. suggesting that the universe might contain wonders beyond what the naked eye could reveal, secrets waiting for those with the patience and the tools to find them. The question of what to name this new world sparked considerable debate. Herschel, ever loyal to his adopted homeland, proposed calling it Georgium Sidus, the Georgian star, in honour of King George III of England. This suggestion was not popular outside of Britain. French astronomers, in particular, had little enthusiasm for naming a planet after the English king. Other names were proposed, including Herschel itself, honouring the discoverer. Eventually, the astronomical community settled on a name from mythology, following the tradition established by the ancients. The new planet would be called Uranus, after the Greek god of the sky. In mythology, Uranus was the father of Saturn, just as Saturn was the father of Jupiter. The name placed the new planet appropriately in the celestial family tree, a generation older and more distant than the ringed giant that had previously marked the boundary of the known solar system. The discovery of Uranus transformed William Herschel's life. King George, flattered by the original proposed name, granted Herschel an annual salary that allowed him to abandon music and devote himself entirely to astronomy. Herschel built ever larger telescopes and continued to make important discoveries, including 2 moons of Uranus and 2 moons of Saturn. He became one of the most celebrated astronomers of his age, all because of that cold March night when he noticed something slightly unusual in the constellation of Gemini. But the story of Uranus was only beginning. As astronomers tracked the planet's slow journey around the Sun, they noticed something troubling. Uranus was not behaving as it should. The mathematics of celestial mechanics, refined by Isaac Newton and his successors, allowed astronomers to predict with great precision where a planet should be at any given time. These predictions accounted for the gravitational pull of the Sun and the other known planets. Yet Uranus consistently deviated from its predicted path. Sometimes it moved slightly faster than expected, sometimes slightly slower. The discrepancies were small but persistent and deeply puzzling. Some astronomers wondered if Newton's laws of gravity might break down at great distances from the Sun. Perhaps the rules that governed motion in the inner solar system did not apply in the cold outer reaches. But there was another possibility, one that would prove correct and would lead to one of the most remarkable achievements in the history of science. Perhaps Uranus was being pulled by the gravity of yet another planet, a world even more distant and even more hidden in the darkness. Before 1781, the solar system was a cosy and familiar place. The planets were old friends, known by name for millennia, their wanderings across the sky recorded by countless generations. The discovery of Uranus revealed that this familiarity was an illusion. The solar system was vast beyond ancient imagination, and it held secrets that no human eye had ever glimpsed. Herschel himself understood the magnitude of what he had found. In his later years, he reflected on the nature of discovery and the humility it should inspire. The universe, he recognized, was far larger and more complex than any single human mind could comprehend. Each discovery only revealed how much more remained unknown. The planet Uranus circles the Sun at an average distance of about 1.8 billion miles, more than 19 times farther from the Sun than Earth. At this immense distance, sunlight is feeble, and the planet exists in a perpetual twilight. A year on Uranus, the time required for one complete orbit, lasts 84 Earth years. Herschel, who lived to the age of 83, did not quite see Uranus complete even one full orbit after its discovery. The discovery also highlighted the importance of technology in expanding human knowledge. Without his telescope, Herschel could never have spotted Uranus. The planet is technically visible to the naked eye under perfect conditions, but it is so faint that no one in recorded history had recognized it as a planet before Herschel. Ancient astronomers had actually observed Uranus on multiple occasions, but they had always assumed it was simply a dim star. Only with optical aid could its true nature be revealed. This lesson would be repeated throughout the history of astronomy. Each advance in technology, from larger telescopes to photography to spectroscopy to space probes, would reveal new wonders that had previously been invisible. The universe, it seemed, always had more to show those who developed better ways of looking. The decades following Herschel's discovery of Uranus were a time of careful observation and growing puzzlement. Astronomers across Europe tracked the new planet's position with meticulous precision, adding each measurement to a growing database of observations. As this database expanded, a troubling pattern emerged. Uranus simply would not stay where the mathematics said it should be. The science of celestial mechanics had reached a high level of sophistication by the early 19th century. Building on the foundations laid by Isaac Newton, mathematicians had developed powerful techniques for predicting planetary motions. These techniques accounted for the gravitational interactions between all the known bodies in the solar system. When applied to the inner planets, they worked beautifully. Mercury, Venus, Earth, Mars, Jupiter, and Saturn all moved in close agreement with theoretical predictions. But Uranus was different. By the 1840s, the discrepancy between Uranus's predicted position and its observed position had grown to about 2 arc minutes, a small angle, but one that was impossible to ignore. Something was affecting Uranus's motion, something that the existing calculations did not account for. 2 possibilities presented themselves. The first was that Newton's law of gravitation might not apply perfectly at great distances from the Sun. Perhaps gravity weakened more rapidly than the inverse square law predicted, or perhaps some other modification was needed. This possibility troubled astronomers deeply, for Newton's laws had proven so successful in so many other contexts. The second possibility was more exciting. Perhaps there was another planet, even more distant than Uranus, whose gravitational pull was responsible for the observed irregularities. If such a planet existed, it might be possible to work backward from the disturbances in Uranus's orbit to determine where this hypothetical planet must be located. This second approach was attempted independently by 2 young mathematicians, one in England and one in France, and their parallel efforts would lead to one of the most celebrated discoveries in scientific history. John Couch Adams was a brilliant student at Cambridge University who became interested in the problem of Uranus's orbit while still an undergraduate. In 1841, at the age of 22, he made a note to himself that he would investigate the irregularities after completing his degree. True to his word, Adams began his calculations in 1843 and worked on them for 2 years. The mathematical challenge was formidable. Adams had to assume the existence of an unknown planet, estimate its mass and distance from the Sun, and then calculate how its gravitational influence would affect Uranus's motion. By comparing these calculated effects with the observed irregularities, he could refine his estimates and gradually zero in on the unknown planet's location. By September 1845, Adams had completed his calculations and believed he knew where the new planet could be found. He wrote to James Challis, the director of the Cambridge Observatory, and to George Airy, the Astronomer Royal, presenting his results. But neither man took immediate action. Challis was busy with other projects, and Airy had doubts about the validity of Adams' approach. The young mathematician's predictions sat unexamined while months passed. Meanwhile, in France, a similar effort was underway. Urbain Le Verrier was a mathematician and astronomer who had already made significant contributions to celestial mechanics. In 1845, the director of the Paris Observatory encouraged him to investigate the problem of Uranus's orbit. Le Verrier threw himself into the work with characteristic intensity. Leverrier's approach was similar to Adams's, though developed entirely independently. He analysed the discrepancies in Uranus's motion, assumed the existence of an exterior planet, and used the mathematics of gravitational perturbation to predict where that planet must be. By the summer of 1846, Leverrier had completed his calculations and was ready to announce his results. On August 31st, 1846, Leverrier presented his predictions to the French Academy of Sciences. He specified the location in the sky where the unknown planet should be found, along with estimates of its mass and orbital characteristics. The announcement created considerable excitement, but French observatories were slow to act. Leverrier, impatient for confirmation, decided to write to an astronomer he had never met, a young man at the Berlin Observatory named Johann Gottfried Galle. Leverrier's letter reached Galle on September 23, 1846. That very night, Galle and his assistant Heinrich d'Arrest turned the Berlin Observatory's telescope toward the position Leverrier had specified. The observatory happened to have recently acquired a new star chart of that region of the sky, a fortunate circumstance that would prove crucial. Galle began calling out the positions and brightnesses of stars in the field of view, while d'Arrest checked each one against the chart. Star after star matched the chart perfectly. Then Galle described an object of the 8th magnitude at a particular position. D'Arrest looked at the chart. There was no star at that location. They had found it. In less than an hour of searching, Galle and d'Arrest had discovered a new planet, within 1 degree of where Leverrier had predicted it would be. The next night, they observed the object again, and confirmed that it had moved against the background stars. There could be no doubt. The solar system had gained another member. The discovery of Neptune was immediately recognized as a triumph of theoretical science. For the first time in history, a major celestial body had been found not by scanning the heavens, but by mathematical prediction. Newton's laws of gravity, far from breaking down at great distances, had been spectacularly confirmed. The human mind, armed with mathematics, had reached across billions of miles of space to locate a world that no eye had ever seen. The question of credit, however, proved contentious. When news of Galle's discovery reached England, astronomers there realized that Adams had made similar predictions months earlier. Why had no one searched for the planet based on Adams's work? Accusations flew back and forth across the English Channel. French astronomers felt that Leverrier deserved sole credit for the discovery, while British astronomers championed Adams as the true discoverer. In time, a consensus emerged that both men deserved recognition. Adams and Leverrier had independently solved the same difficult problem using similar methods. The failure of British astronomers to act on Adams' predictions was a failure of the scientific establishment, not of Adams himself. Today, both mathematicians are honoured as co-predictors of Neptune, a shared credit that reflects the reality of their parallel achievements. The naming of the new planet followed a now familiar pattern of initial disagreement followed by mythological resolution. Leverrier initially wanted to name the planet after himself, a suggestion that found little support outside France. Other names were proposed, including Janus and Oceanus. Eventually the name Neptune was adopted, honouring the Roman god of the sea. The name was fitting for a world that would later reveal its deep blue colour, reminiscent of Earth's oceans. Neptune orbits the Sun at an average distance of about 2.8 billion miles, more than 30 times farther from the Sun than Earth. At this immense distance, the Sun appears as little more than a very bright star, and temperatures plunge to hundreds of degrees below zero. A year on Neptune, the time required for one complete orbit, lasts about 165 Earth years. Neptune has not yet completed a single orbit since its discovery in 1846. The discovery of Neptune had profound implications for the philosophy of science. It demonstrated that mathematical reasoning, properly applied, could reveal truths about the physical world that were inaccessible to direct observation. The universe, it seemed, was rational and lawful, governed by principles that the human mind could discover and apply. This confidence in the power of mathematics would inspire generations of scientists. If Neptune could be found through calculation, what other secrets might mathematics unlock? The discovery encouraged a view of the cosmos as a vast machine operating according to precise mathematical laws that patient investigation could reveal. But the discovery also raised new questions. Were there more planets beyond Neptune? The solar system had proven larger than anyone had imagined, first with Uranus and now with Neptune. Perhaps the pattern would continue, with ever more distant worlds waiting in the darkness. This question would drive astronomical research for decades. The search for a ninth planet would eventually lead to the discovery of Pluto in 1930, though Pluto would later be reclassified as a dwarf planet. The outer solar system, it turned out, was far more complex and populated than the simple picture of 8 or 9 major planets suggested. For now, though, let us appreciate the elegance of Neptune's discovery. 2 young mathematicians, working independently on opposite sides of the English Channel, had used nothing but pen, paper, and the laws of physics to locate a world billions of miles away. Their achievement stands as one of the great intellectual triumphs in human history, a testament to the power of reason and the deep mathematical structure of the universe. For many years after their discoveries, Uranus and Neptune were grouped together with Jupiter and Saturn as the giant planets of the outer solar system. All 4 were known to be much larger than the rocky inner planets, and all 4 were assumed to be similar in composition, great balls of gas surrounding relatively small cores. But as our understanding of these distant worlds deepened, a more nuanced picture emerged. Uranus and Neptune, it turns out, are fundamentally different from their larger cousins. They belong to a distinct category that scientists now call ice giants. The term ice giant can be misleading if taken too literally. When planetary scientists speak of ice in this context, they do not mean frozen water in the familiar sense of ice cubes or glaciers. Instead, they refer to a class of chemical compounds that includes water, ammonia, and methane. These substances are called ices because they would be frozen solid at the temperatures found in the outer solar system, far from the warmth of the sun. In the interiors of Uranus and Neptune, however, these ices exist under such extreme pressures and temperatures that they take on exotic forms quite unlike anything we experience on Earth. The distinction between gas giants and ice giants lies in their composition and internal structure. Jupiter and Saturn are composed primarily of hydrogen and helium, the 2 lightest and most abundant elements in the universe. These planets formed in regions of the solar nebula where hydrogen and helium were plentiful, and their powerful gravity allowed them to capture and retain enormous quantities of these gases. As a result, Jupiter and Saturn are essentially giant balls of hydrogen and helium, with relatively small cores of heavier elements at their centres. Uranus and Neptune tell a different story. While they do possess outer atmospheres of hydrogen and helium, these gases make up a much smaller fraction of their total mass. The bulk of each planet consists of heavier elements, particularly the ices of water, ammonia, and methane. Current models suggest that ices and rocks account for about 80 to 90% of the mass of Uranus and Neptune, compared to perhaps 10 to 20% for Jupiter and Saturn. This compositional difference reflects the conditions under which these planets formed. In the early solar system, the region where Uranus and Neptune coalesced was colder and less dense than the regions closer to the Sun. Hydrogen and helium, being so light, were more easily swept away by the solar wind and other processes. The heavier ices, however, remained available as building blocks. Uranus and Neptune grew by accumulating these icy materials, eventually becoming large enough to capture some hydrogen and helium, but never achieving the massive gas envelopes of Jupiter and Saturn. The sizes of the ice giants reflect their intermediate status. Uranus has a diameter of about 31,500 miles, roughly 4 times the diameter of Earth. Neptune is slightly smaller in diameter at about 30,600 miles, but is actually more massive than Uranus, indicating a higher density and a greater proportion of heavy elements. Both planets are much smaller than Jupiter, which has a diameter of about 86,900 miles, and Saturn, which measures about 72,400 miles across. In terms of mass, the difference is even more striking. Jupiter contains about 318 times the mass of Earth, while Saturn contains about 95 Earth masses. Uranus, by contrast, has only about 14.5 Earth masses, and Neptune has about 17 Earth masses. The ice giants are thus intermediate in size between the rocky inner planets and the gas giants, a distinct category with its own characteristics and mysteries. The colours of Uranus and Neptune provide a visible clue to their composition. Both planets appear blue or blue-green when observed from space, a striking contrast to the browns and tans of Jupiter and the pale gold of Saturn. This blue colour results from methane in the planet's atmospheres. Methane gas absorbs red light from the sun, while allowing blue light to scatter back into space. The more methane in the atmosphere, the deeper and more vivid the blue colour. Neptune appears a more intense blue than Uranus, even though both planets have similar amounts of methane in their atmospheres. Scientists believe that Neptune's atmosphere contains some additional compound that absorbs red light, enhancing the blue colour, but the exact identity of this compound remains uncertain. This is one of many mysteries that future missions to the ice giants might help solve. The internal structures of Uranus and Neptune are subjects of ongoing research and debate. Because we cannot see beneath the cloud tops, scientists must infer what lies inside based on indirect evidence such as the planet's masses, sizes, gravitational fields, and magnetic fields. Current models suggest a layered structure, though the boundaries between layers may be gradual rather than sharp. At the centre of each ice giant lies a core of rock and metal, probably similar in composition to the rocky inner planets. This core may have a mass equivalent to 1 or 2 Earths. Surrounding the core is a thick mantle of ices, water, ammonia, and methane, compressed to incredible densities by the weight of the overlying layers. This mantle is not solid ice in any familiar sense. Under the extreme pressures found deep within these planets, the ices behave as hot, dense fluids, perhaps better described as a vast ocean of exotic matter. Above the mantle lies the atmosphere, composed primarily of hydrogen and helium with traces of methane and other compounds. The atmosphere extends from the visible cloud tops down to depths where pressure and temperature rise to the point that the gas gradually transitions into the denser mantle below. There is no sharp surface, no boundary where one could stand. The atmosphere simply becomes denser and hotter with depth until it merges with the mantle. One of the most intriguing possibilities suggested by models of ice giant interiors is the existence of diamond rain. Deep within Uranus and Neptune, where pressures reach millions of times Earth's atmospheric pressure and temperatures soar to thousands of degrees, methane molecules may be torn apart. The carbon atoms released from this destruction could bond together to form diamonds, which would then sink slowly through the surrounding material like rain falling through air. These diamonds might eventually accumulate in a layer around the rocky core, creating a shell of crystalline carbon surrounding the heart of the planet. This idea of diamond rain captures the imagination, but it remains theoretical. We have no way to directly observe the deep interiors of Uranus and Neptune, and laboratory experiments can only approximate the extreme conditions found there. The true nature of these planetary interiors remains one of the great unsolved puzzles of planetary science. The ice giants also differ from the gas giants in their energy budgets. Jupiter and Saturn both radiate significantly more heat into space than they receive from the Sun. This excess heat is thought to come from the slow gravitational contraction of these planets, a process that converts gravitational potential energy into thermal energy. Neptune also radiates more heat than it receives, about 2.6 times as much, suggesting that it too has an internal heat source. Uranus, however, is an anomaly. It radiates very little excess heat, barely more than it receives from the Sun. This is puzzling because Uranus and Neptune are so similar in size and composition that one would expect their internal heat budgets to be similar as well. Why is Uranus so cold inside? Uranus holds a special place among the planets of our solar system. Not only as the first planet discovered in modern times, but also as perhaps the strangest. While every planet has its peculiarities, Uranus possesses a characteristic so extreme and so unusual that it sets this world apart from all others. Uranus is tilted on its side. Every planet rotates on an axis, an imaginary line running through its poles around which the planet spins. For most planets, this axis is roughly perpendicular to the plane of the planet's orbit, tilted only modestly from vertical. Earth's axis, for example, is tilted about 23.5 degrees from perpendicular, enough to give us seasons but not enough to dramatically alter the basic geometry of day and night. Jupiter's axis is tilted only about 3 degrees, Saturn's about 27 degrees, and Neptune's about 28 degrees. Uranus, however, has an axial tilt of about 98 degrees. This means that the planet's axis lies almost in the plane of its orbit, as if Uranus had been knocked onto its side. The consequences of this extreme tilt are profound and far-reaching, affecting the planet's seasons, its day-night cycle, and even the behaviour of its moons and rings. Imagine standing on the cloud tops of Uranus at one of the poles. For about 42 Earth years, roughly half of a Uranian year, your pole would point almost directly toward the Sun. The Sun would spiral slowly around the sky, never setting, while the opposite pole remained in continuous darkness. Then, as Uranus continued along its orbit, the situation would reverse. Your pole would point away from the Sun, plunging into 42 years of continuous night, while the other pole enjoyed its decades-long day. Imagine standing on the cloud tops of Uranus at one of the poles. For about 42 Earth years, roughly half of a Uranian year, your pole would point almost directly toward the Sun. The Sun would spiral slowly around the sky, never setting, while the opposite pole remained in continuous darkness. Then, as Uranus continued along its orbit, the situation would reverse. Your pole would point away from the Sun, plunging into 42 years of continuous night, while the other pole enjoyed its decades-long day. The equatorial regions of Uranus experience a different but equally strange pattern. Twice during each Uranian year, when the planet reaches the points in its orbit where neither pole points toward the Sun, the equator faces the Sun directly. During these brief equinox periods, Uranus experiences something resembling a normal day-night cycle, with the Sun rising and setting every 17 hours as the planet rotates. But these periods of relative normalcy are fleeting interruptions in a lifetime of extremes. This bizarre axial tilt raises an obvious question. How did Uranus end up this way? Planets are thought to form from rotating disks of gas and dust, and the physics of this process tends to produce planets with axes roughly perpendicular to their orbital planes. Something must have happened to Uranus to knock it so dramatically off kilter. The leading explanation involves a catastrophic collision early in the solar system's history. According to this theory, a massive object Perhaps an Earth-sized protoplanet struck Uranus with tremendous force during the chaotic period when the planets were still forming. This impact would have been violent enough to tip Uranus onto its side, while leaving the planets otherwise intact. Computer simulations support this scenario. Researchers have modelled impacts of various sizes and angles, finding that a collision with an object 1 to 3 times Earth's mass could indeed produce Uranus's current tilt. Some simulations suggest a single, massive impact, while others propose a series of smaller collisions that cumulatively tilted the planets. The exact details remain uncertain, but the impact hypothesis is widely accepted as the most plausible explanation. An alternative theory suggests that Uranus might have been tilted by gravitational interactions with other planets during a period of orbital instability early in the solar system's history. According to this view, the giant planets may have migrated significantly from their original positions, and close encounters between them could have altered their axial tilts. However, this mechanism struggles to explain why Uranus is tilted so much more than the other giant planets, making the impact hypothesis more compelling. The extreme tilt of Uranus has consequences that extend beyond the planet itself. The moons of Uranus orbit in the plane of the planet's equator, which means they too circle in a plane nearly perpendicular to Uranus's orbital plane. As Uranus moves around the Sun, its moons trace out orbits that sometimes appear nearly face-on from our perspective, and sometimes appear edge-on. The same is true of Uranus's rings, which encircle the planet's equator and share its extreme tilt. When Voyager 2 flew past Uranus in January 1986, the planet's south pole was pointing almost directly at the Sun. This meant that the spacecraft approached Uranus from a direction that looked down on the ring system and the orbits of the moons, providing excellent views of these features. But it also meant that the entire southern hemisphere of Uranus was in continuous sunlight, while the northern hemisphere was hidden in darkness. Voyager could only photograph half the planet in detail. The appearance of Uranus through a telescope is notably bland compared to the other giant planets. Jupiter displays colourful bands and swirling storms, most famously the Great Red Spot. Saturn shows subtler banding and occasional white storms. Even Neptune, as we shall see, displays visible atmospheric features. But Uranus appears as an almost featureless blue-green disk, with little to catch the eye. This apparent blandness puzzled scientists for many years. With its extreme seasons and tilted orientation, one might expect Uranus to display dramatic atmospheric activity. Instead, the planet seemed almost comatose, its atmosphere calm and uniform. Several factors may contribute to this apparent tranquility. One factor is the low amount of internal heat that Uranus radiates. As mentioned earlier, Uranus emits very little more energy than it receives from the Sun, unlike the other giant planets. This lack of internal heat means less energy is available to drive atmospheric circulation and storm formation. The atmosphere may be more stable and less turbulent as a result. Another factor is the extreme nature of Uranian seasons. When one pole points toward the Sun for decades at a time, the atmospheric circulation patterns may be fundamentally different from those on planets with more conventional tilts. The atmosphere may settle into a relatively stable configuration that produces few visible features. However, more recent observations have revealed that Uranus is not as bland as it first appeared. As the planet has moved along its orbit and its orientation relative to Earth has changed, astronomers have observed cloud features, storms, and atmospheric banding that were not visible during the Voyager encounter. In 2014, astronomers using the Keck Observatory in Hawaii observed a series of bright storms in Uranus's atmosphere, the most active weather ever seen on the planet. These observations suggest that Uranus's atmosphere may become more active as the planet approaches equinox, when sunlight falls more evenly on both hemispheres. The changing seasons may drive atmospheric dynamics that are not apparent when one pole is pointed directly at the sun. Uranus, it seems, is not as sleepy as it once appeared. The rotation of Uranus presents its own mysteries. The planet rotates once every 17 hours and 14 minutes, giving it a day slightly shorter than a day on Saturn or Neptune. This rotation is retrograde, meaning that Uranus spins in the opposite direction from most other planets when viewed from above its orbital plane. However, because of the extreme axial tilt, the definition of retrograde becomes somewhat arbitrary. Depending on how you define the planet's north pole, Uranus could be said to rotate either prograde or retrograde. The magnetic field of Uranus is one of the planet's most peculiar features. Most planets with significant magnetic fields have their magnetic poles located relatively close to their rotational poles. Earth's magnetic poles, for example, are offset from the rotational poles by only about 11 degrees. This alignment makes intuitive sense, as planetary magnetic fields are thought to be generated by convection currents in electrically conducting fluid regions, and these currents are influenced by the planet's rotation. Uranus breaks this pattern dramatically. The planet's magnetic field is tilted about 59 degrees from its rotational axis, and the centre of the magnetic field is offset from the centre of the planet by about 1/3 of the planet's radius. This means that the magnetic field is not only tilted but also lopsided, stronger on one side of the planet than the other. This strange magnetic field geometry may result from the unusual internal structure of Uranus. Rather than being generated in a metallic hydrogen core like Jupiter's magnetic field, the magnetic field of Uranus may be produced in a relatively thin shell of electrically conducting fluid, perhaps a layer of ionized water or ammonia at intermediate depths. The dynamics of this conducting layer, influenced by the planet's strange tilt and rotation, may produce the offset and tilted magnetic field that we observe. The magnetosphere of Uranus, the region of space dominated by the planet's magnetic field, has a complex and ever-changing shape. Because the magnetic axis is so tilted relative to the rotational axis, the magnetosphere wobbles dramatically as the planet rotates. Every 17 hours, the magnetic poles swing around, causing the magnetosphere to twist and deform in ways not seen at any other planet. Uranus possesses a system of rings, though they are far less spectacular than Saturn's famous rings. The rings of Uranus were discovered in 1977, not through direct observation, but through a technique called stellar occultation. Astronomers were watching as Uranus passed in front of a distant star, hoping to learn about the planet's atmosphere by observing how it affected the star's light. Before and after the planet blocked the star, the astronomers noticed brief dips in the star's brightness. These dips indicated that something was blocking the starlight before and after the planet itself passed in front of the star. That something was the rings. Subsequent observations revealed a system of narrow, dark rings encircling Uranus. Unlike Saturn's broad, bright rings, the rings of Uranus are thin and composed of very dark material that reflects little sunlight. The largest and most prominent ring, called the Epsilon ring, is only about 60 miles wide, but is relatively bright compared to the others. The rings are thought to be composed of water ice mixed with dark organic compounds, giving them their low reflectivity. Voyager 2 provided our best views of the Uranian rings, revealing additional faint rings not visible from Earth. The total number of known rings now stands at 13, though the exact count depends on how one defines a distinct ring versus a component of a larger structure. The rings are thought to be relatively young, perhaps only a few 100 million years old, and maybe the debris from moons that were shattered by impacts or torn apart by tidal forces. The overall appearance of Uranus, with its blue-green colour, tilted orientation, dark rings, and retinue of moons, makes it one of the most distinctive objects in the solar system. This is a world that defies expectations, a planet that seems to have been assembled according to different rules than its neighbours. As we prepare to leave Uranus and journey onward to Neptune, take a moment to appreciate the strangeness of this tilted world. Here is a planet where seasons last for decades, where the magnetic field is askew, where dark rings circle a sideways equator, and where the feeble light of the distant sun creates patterns of day and night unlike anything else in the solar system. Neptune, the eighth and outermost planet of our solar system, drifts through the darkness at an almost inconceivable distance from the sun. At an average distance of 2.8 billion miles, Neptune receives only about 1/900th the sunlight that Earth enjoys. The sun, seen from Neptune, would appear as little more than an intensely bright star, providing light but precious little warmth. In this remote and frigid realm, one might expect to find a frozen, static world, a planet where the cold has stilled all motion and silenced all activity. Nothing could be further from the truth. Neptune is one of the most dynamic and violent worlds in the solar system, a planet racked by storms and winds that dwarf anything found on Earth or even on Jupiter. The blue giant at the edge of the solar system is a world of perpetual tempest, where the atmosphere churns with an energy that seems to defy the feeble sunlight that reaches it. The deep blue colour of Neptune is the first thing that strikes any observer. This blue is more vivid and more intense than the paler blue-green of Uranus, giving Neptune a jewel-like appearance that has captivated astronomers since the planet was first observed through powerful telescopes. Like Uranus, Neptune owes its blue colour to methane in its atmosphere, which absorbs red light and reflects blue. But Neptune's blue is deeper and richer, suggesting the presence of some additional colouring agent that scientists have not yet identified. When Voyager 2 flew past Neptune in August 1989, it revealed an atmosphere far more active than anyone had anticipated. The most striking feature was a massive storm system that scientists named the Great Dark Spot. This oval-shaped disturbance was roughly the size of Earth, a vast cyclonic system that rotated counterclockwise in Neptune's southern hemisphere. The Great Dark Spot bore some resemblance to Jupiter's Great Red Spot, and scientists initially wondered if it might be a similarly long-lived feature. But Neptune's Great Dark Spot proved to be ephemeral. When the Hubble Space Telescope observed Neptune in 1994, just 5 years after the Voyager encounter, the Great Dark Spot had vanished. In its place, new storm systems had appeared in different locations. Neptune's atmosphere, it seems, is so dynamic that even its largest features come and go on timescales of years. The winds of Neptune are the fastest in the solar system. Near the equator, winds blow westward at speeds approaching 1,200 miles per hour, faster than the speed of sound in Neptune's atmosphere. These winds are retrograde, meaning they blow in the opposite direction to the planet's rotation. At higher latitudes, the winds shift to blow eastward, creating a complex pattern of atmospheric circulation. The existence of such powerful winds on Neptune presents a puzzle. Winds are driven by energy, and on most planets, that energy comes ultimately from the sun. But Neptune receives so little sunlight that solar heating alone cannot explain the ferocity of its winds. The answer lies in Neptune's internal heat. Unlike Uranus, Neptune radiates significantly more energy than it receives from the sun, about 2.6 times as much. This excess energy comes from the planet's interior, heat left over from Neptune's formation and possibly generated by ongoing processes such as gravitational settling of heavier materials. This internal heat drives convection in the atmosphere, which in turn powers the planet's remarkable winds. The contrast with Uranus is striking. Despite their similar sizes and compositions, Neptune is far more meteorologically active than its neighbour. The difference in internal heat appears to be the key factor. Uranus, with its minimal internal heat, has a relatively calm atmosphere, while Neptune, with its substantial internal heat source, churns with constant activity. Neptune's atmosphere displays a variety of features beyond the great storm systems. Bright white clouds of methane ice form at high altitudes, casting shadows on the deeper cloud layers below. These clouds form and dissipate rapidly, changing from day to day as observed from Earth. Bands of different colours and brightnesses encircle the planet, indicating variations in atmospheric composition or cloud altitude at different latitudes. The structure of Neptune's atmosphere follows the general pattern of the other giant planets. The visible cloud tops give way to ever denser layers of gas as one descends into the planet. Hydrogen and helium dominate the upper atmosphere, with methane contributing the characteristic blue colour. Deeper down, the atmosphere gradually transitions into the denser mantle of ices that makes up the bulk of the planet. Neptune rotates once every 16 hours and 6 minutes, giving it the shortest day of any giant planet. This rapid rotation, combined with the internal heat that drives atmospheric convection, helps explain the planet's dynamic weather. The Coriolis effect, which deflects moving air masses due to planetary rotation, is strong on Neptune and contributes to the formation of the banded structure and rotating storm systems. The magnetic field of Neptune shares some characteristics with that of Uranus. Like Uranus, Neptune has a magnetic field that is tilted dramatically from its rotational axis, about 47 degrees, and offset from the planet's centre by about half the planet's radius. This strange geometry suggests that Neptune's magnetic field, like that of Uranus, is generated in a shell of conducting fluid at intermediate depths rather than in a central core. The similar magnetic field configurations of Uranus and Neptune support the idea that these ice giants have fundamentally different internal structures from the gas giants Jupiter and Saturn. The magnetic fields provide indirect evidence about the planet's interiors, and the unusual fields of the ice giants suggest unusual internal arrangements. Neptune's magnetosphere interacts with the solar wind, the stream of charged particles flowing outward from the Sun, to create a complex environment of trapped particles and electromagnetic phenomena. The magnetosphere is compressed on the sunward side and stretched into a long tail on the night side, similar to Earth's magnetosphere, but on a vastly larger scale. The planet is encircled by a system of rings, though like the rings of Uranus, they are faint and dark compared to Saturn's brilliant rings. Neptune's rings were suspected before the Voyager encounter based on stellar occultation observations, but their nature was unclear. Some observations suggested that the rings might be incomplete arcs rather than full circles, a configuration that would be dynamically unstable and difficult to explain. Voyager 2 resolved this mystery by revealing that Neptune does indeed have complete rings, but some portions of the rings are much denser than others, creating the appearance of arcs when viewed from Earth. The brightest of these ring arcs were given names: Liberté, Égalité, and Fraternité, honouring the motto of the French Revolution and acknowledging the French contribution to Neptune's discovery. The rings of Neptune are composed of dust and small particles, probably created by the impacts of micrometeoroids on small moons orbiting within or near the ring system. The rings are thought to be relatively young and may be continuously replenished by ongoing collisions. Without this replenishment, the rings would spread out and dissipate over millions of years. The smaller moons of Neptune include Nereid, discovered in 1949, which has one of the most eccentric orbits of any moon in the solar system. Nereid's orbit takes it from about 841,000 miles from Neptune at its closest approach to about 5.9 million miles at its most distant, a range that suggests the moon's orbit was disrupted by some past event, possibly the capture of Triton. The other small moons of Neptune were mostly discovered by Voyager 2 or by ground-based observations in subsequent years. These moons are small, irregular bodies, probably captured asteroids or Kuiper belt objects that wandered too close to Neptune and were snared by its gravity. Neptune's position at the outer edge of the planetary solar system gives it a special role in the architecture of our cosmic neighbourhood. Beyond Neptune lies the Kuiper belt, a vast region of icy bodies left over from the formation of the solar system. Neptune's gravity has shaped the Kuiper belt over billions of years, clearing some regions while concentrating objects in others. Some Kuiper belt objects are in orbital resonance with Neptune, meaning their orbital periods are related to Neptune's by simple ratios. Pluto, for example, completes 2 orbits for every 3 that Neptune completes. This resonance protects Pluto from close encounters with Neptune, even though their orbits cross when viewed from above. Neptune's gravitational influence extends far beyond its immediate vicinity. The planet is thought to have played a crucial role in the early evolution of the solar system, possibly migrating outward from a closer initial position and scattering smaller bodies throughout the outer solar system in the process. This migration may have triggered the late heavy bombardment, a period of intense cratering that affected all the inner planets about 3.9 billion years ago. As we conclude our exploration of Neptune's basic characteristics, take a moment to marvel at this distant blue world. Here is a planet that defies expectations at every turn. Despite receiving almost no warmth from the sun, it generates enough internal heat to power the fastest winds in the solar system. Despite its serene blue appearance, it hosts storms that could swallow the Earth. Despite its remote location, it has shaped the structure of the outer solar system through its gravitational influence. Neptune represents the frontier of the planetary solar system, the last of the major worlds before the vast emptiness of interstellar space begins. Beyond Neptune, the sun's influence gradually fades, and the darkness between stars takes over. But Neptune itself is anything but empty or inactive. It is a world of beauty and violence, calm blue surfaces hiding turbulent depths. Both ice giants possess atmospheres composed primarily of hydrogen and helium, the 2 lightest and most abundant elements in the universe. Hydrogen accounts for roughly 80 to 83% of the atmospheric molecules, while helium makes up about 15 to 18%. These proportions are similar to those found in the atmospheres of Jupiter and Saturn, reflecting the common origin of all 4 giant planets from the hydrogen-rich solar nebula. The remaining few percent of the atmosphere consists of heavier molecules that, despite their small abundances, have outsized effects on the planet's appearances and behaviours. Methane is the most important of these trace constituents, accounting for about 2 to 3% of the atmosphere. It is methane that gives both planets their distinctive blue colours by absorbing red light and allowing blue light to scatter back into space. The process by which methane creates the blue colour is straightforward. Sunlight entering the atmosphere contains all the colours of the visible spectrum, from red through orange, yellow, green, blue, and violet. As this light penetrates into the atmosphere, methane molecules absorb the red and orange wavelengths, removing them from the light. The remaining blue and green wavelengths scatter off gas molecules and cloud particles, eventually escaping back into space, where they can be observed from Earth. The depth of the blue colour depends on how much methane the light encounters before escaping. Neptune's deeper blue suggests that its atmosphere may have slightly more methane than Uranus's, or that the scattering occurs at greater depths where more absorption has taken place. Some scientists have proposed that Neptune's atmosphere contains an additional absorbing compound, perhaps a photochemical product created when ultraviolet light breaks down methane. But this hypothesis remains unconfirmed. Beyond methane, the atmospheres contain traces of other hydrocarbons produced by the photochemical destruction of methane in the upper atmosphere. Ultraviolet light from the sun breaks apart methane molecules, and the resulting fragments can recombine to form more complex hydrocarbons such as ethane and acetylene. These compounds are present in small amounts but can be detected through spectroscopy, the analysis of light absorbed or emitted at specific wavelengths. The vertical structure of the atmospheres follows a pattern familiar from other planets. At the highest altitudes lies the thermosphere, a region where temperatures actually increase with altitude due to absorption of solar ultraviolet radiation. Below this is the stratosphere, where temperatures decrease with altitude. The stratosphere contains most of the photochemically produced hydrocarbons, which absorb ultraviolet light and help create the temperature inversion that defines this layer. Below the stratosphere lies the troposphere, the lowest and densest layer of the atmosphere. In the troposphere, temperature decreases with altitude at a rate determined by the properties of the atmospheric gases. This is the region where weather occurs, where clouds form and dissipate, and where the winds that we observe at the cloud tops have their origins. The cloud structures of Uranus and Neptune are layered, with different types of clouds forming at different altitudes depending on the temperature and pressure. The highest clouds are composed of methane ice, forming in the cold upper troposphere, where temperatures drop low enough for methane to condense. These methane clouds appear as bright white features against the blue background of the deeper atmosphere. Deeper in the atmosphere, where temperatures are warmer, other cloud layers are thought to exist. Hydrogen sulfide clouds may form at intermediate levels, while water clouds may exist at still greater depths. However, these deeper cloud layers are difficult to observe directly because the overlying atmosphere absorbs much of the light that would reveal them. The temperature profiles of Uranus and Neptune differ in important ways that reflect the planet's different internal heat budgets. Neptune's atmosphere is warmer than Uranus's at comparable pressure levels, despite Neptune being farther from the Sun and receiving less solar radiation. This warmth comes from Neptune's substantial internal heat source, which pumps energy into the atmosphere from below. Uranus, with its minimal internal heat, has a colder atmosphere that is more directly controlled by the feeble solar heating it receives. The lack of internal heat may also explain why Uranus's atmosphere appears more uniform and less active than Neptune's. Without a strong heat source driving convection from below, the atmosphere settles into a more stable configuration. The wind patterns on both planets reveal the complex dynamics of their atmospheres. As mentioned earlier, Neptune has the fastest winds in the solar system, with equatorial winds blowing westward at nearly 1,200 miles per hour. Uranus also has strong winds, though not quite as extreme, with equatorial winds reaching about 560 miles per hour in the retrograde direction. Both planets show a pattern of retrograde winds at the equator and prograde winds at higher latitudes. This pattern differs from that seen on Jupiter and Saturn, where the equatorial winds blow in the prograde direction. The reason for this difference is not fully understood, but may relate to the different internal structures and heat distributions of the ice giants compared to the gas giants. The atmospheric circulation on Uranus is further complicated by the planet's extreme axial tilt, with the poles alternately pointing toward and away from the Sun Over the course of an 84-year orbit, the pattern of solar heating varies dramatically over time. One might expect this to produce dramatic seasonal changes in atmospheric circulation, but observations have not clearly detected such changes. The atmosphere may respond slowly to seasonal forcing, or the effects may be subtle and difficult to observe from Earth. Storm systems on both planets provide windows into atmospheric dynamics. Neptune's Great Dark Spot, observed by Voyager 2, was a massive anticyclonic storm, similar in some ways to Jupiter's Great Red Spot. The storm appeared as a dark oval surrounded by bright methane clouds that formed as air rose along the storm's edges and cooled to the point where methane condensed. The disappearance of the Great Dark Spot within a few years of its discovery showed that Neptune's storms are transient features, unlike the centuries-old Great Red Spot on Jupiter. Subsequent observations have revealed other dark spots on Neptune, appearing and disappearing on timescales of years. The atmosphere seems to be in a constant state of reorganization, with storm systems forming, evolving, and dissipating in an ongoing cycle. Uranus shows less dramatic storm activity, but it is not entirely quiescent. Bright cloud features have been observed, particularly as the planet approached its 2007 equinox, when both hemispheres received roughly equal sunlight. These clouds may represent convective storms driven by the changing pattern of solar heating. The increased activity around equinox suggests that Uranus's atmosphere does respond to seasonal changes, even if the response is more subtle than on Neptune. The upper atmospheres of both planets present their own mysteries. The thermospheres of Uranus and Neptune are much hotter than can be explained by solar heating alone. On Uranus, thermospheric temperatures reach about 800 Kelvin, while on Neptune they reach about 750 Kelvin. These temperatures are far higher than models predict based on the amount of solar ultraviolet radiation absorbed at these altitudes. This excess heating is sometimes called the energy crisis of the giant planets because it affects all 4 giant planets, not just the ice giants. Several mechanisms have been proposed to explain the extra heat, including energy deposition from charged particles in the magnetosphere, dissipation of atmospheric waves propagating upward from below, and redistribution of heat from the sunlit to the dark hemispheres. The true explanation may involve a combination of these processes, but the details remain unclear. The chemical composition of the atmospheres provides clues about the formation and evolution of the ice giants. The abundances of various elements and isotopes can be compared to solar abundances and to the compositions of other solar system bodies to infer where and how the planets formed. Both Uranus and Neptune appear to be enriched in heavy elements compared to the Sun, consistent with the idea that they formed from solid icy and rocky materials that accumulated in the outer solar nebula. The degree of enrichment varies for different elements, providing constraints on formation models. However, our knowledge of atmospheric composition is incomplete, and future missions with more sensitive instruments could reveal important new information. The hazes that pervade the upper atmospheres of both planets affect their appearances and complicate efforts to study deeper layers. These hazes are composed of tiny particles, probably hydrocarbons produced by photochemical reactions that scatter and absorb light. The hazes give the atmospheres a somewhat hazy or smoggy quality and make it difficult to see clearly to great depths. On Uranus, the haze appears to be thicker than on Neptune, contributing to the planet's more uniform and featureless appearance. The haze may act like a veil, obscuring cloud features and atmospheric structures that would otherwise be visible. Neptune's thinner haze allows more of the underlying atmosphere to be seen, which may partly explain why Neptune appears more dynamic and feature-rich than Uranus. As we conclude this exploration of the ice giant atmospheres, it is worth reflecting on how much remains unknown. We have observed these atmospheres from Earth and from a single spacecraft flyby, but our understanding is still fragmentary. The vertical structure of the clouds, the composition of the deep atmosphere, the mechanisms driving the winds and storms, the sources of upper atmospheric heating, all of these remain active areas of research with many unanswered questions. For now, let the image of these blue atmospheres fill your mind. Picture the methane clouds drifting across the blue background, the dark storms swirling and dissipating, the winds howling at supersonic speeds through the cold and darkness. These atmospheres are alien and beautiful, familiar in some ways, yet profoundly different from anything we experience on Earth. Beneath the blue cloud tops of Uranus and Neptune lie hidden realms that no human eye will ever see and no spacecraft will ever visit. The interiors of these ice giants are places of extreme pressure and temperature, where familiar substances take on unfamiliar forms and where the very concept of a surface becomes meaningless. The challenge of studying planetary interiors is fundamental. We cannot see through the thick atmospheres to the depths below. We cannot send probes to survive the crushing pressures. We must rely on indirect methods, measuring properties that can be observed from outside and using physics and chemistry to infer what lies within. The most basic constraint on interior structure comes from the planet's masses and sizes. Uranus has a mass of about 14.5 Earth masses and a radius of about 15,800 miles. Neptune has a mass of about 17 Earth masses and a radius of about 15,300 miles. From these measurements we can calculate the average densities, about 1.27 grams per cubic centimetre for Uranus and about 1.64 grams per cubic centimetre for Neptune. These densities tell us immediately that the ice giants cannot be composed entirely of hydrogen and helium, which are too light to produce such densities even when compressed by the planet's gravity. The planets must contain substantial amounts of heavier materials. The higher density of Neptune compared to Uranus, despite their similar sizes, suggests that Neptune has a greater proportion of heavy elements. The gravitational fields of the planets provide additional information. A planet's gravity is not perfectly uniform. It varies slightly depending on the distribution of mass within the planet. By precisely tracking the motions of spacecraft or natural satellites, scientists can measure these gravitational variations and use them to constrain interior structure. The Voyager 2 flybys provided valuable gravitational data for both ice giants. The magnetic fields also offer clues about the interiors. As discussed earlier, both Uranus and Neptune have unusual magnetic fields that are tilted from their rotational axes and offset from their centres. These strange configurations suggest that the magnetic fields are generated in unusual ways, perhaps in thin shells of conducting fluid rather than in central cores, as on Jupiter and Earth. Combining all available evidence, scientists have developed models of ice giant interiors that share some common features while differing in details. The general picture involves three main regions: a relatively small rocky core at the centre, a thick mantle of ices surrounding the core, and a gaseous envelope of hydrogen and helium at the top. The rocky core is thought to be composed of silicate rocks and metals, similar in composition to the rocky inner planets. The core may have a mass equivalent to about 1 Earth mass, though estimates vary. At the centre of the core, pressures reach millions of times Earth's atmospheric pressure, and temperatures may exceed 10,000 degrees Fahrenheit. Under these conditions, the rock may be partially molten or may exist in exotic high-pressure phases not found on Earth's surface. Surrounding the core is the mantle, which makes up the bulk of each planet's mass. The mantle is composed of ices, primarily water, ammonia and methane. However, the term ice is misleading here. Under the extreme pressures and temperatures of the mantle, these substances do not exist as familiar frozen solids. Instead, they form hot, dense fluids that behave in complex ways. Water in the mantle exists in a state sometimes called superionic ice. In this exotic phase, the oxygen atoms are locked in a crystalline lattice, while the hydrogen atoms flow freely through the lattice like a liquid. Superionic water conducts electricity, which may be important for generating the planet's magnetic fields. Laboratory experiments have confirmed that water can enter the superionic phase at the pressures and temperatures expected in ice giant interiors. The behavior of methane under extreme conditions has attracted particular attention because of the possibility of diamond formation. When methane is subjected to the pressures and temperatures, found water in the mantle exists in a state sometimes called superionic ice. In this exotic phase, the oxygen atoms are locked in a crystalline lattice while the hydrogen atoms flow freely through the lattice like a liquid. Superionic water conducts electricity, which may be important for generating the planet's magnetic fields. Laboratory experiments have confirmed that water can enter the superionic phase at the pressures and temperatures expected in ice giant interiors. The behavior of methane under extreme conditions has attracted particular attention because of the possibility of diamond formation. When methane is subjected to the pressures and temperatures found deep within Uranus and Neptune, the molecules can be torn apart. The hydrogen atoms are stripped away, leaving carbon atoms free to bond with one another. Under sufficient pressure, these carbon atoms arrange themselves into the crystalline structure of diamond. Laboratory experiments have demonstrated this process. Scientists have used powerful lasers to compress and heat samples of hydrocarbon materials to conditions similar to those in ice giant interiors. They observed the formation of tiny diamonds, confirming that the physics allows for diamond creation under these extreme conditions. The diamonds formed in the laboratory were microscopic, but the process operating continuously over billions of years inside a planet could produce much larger crystals. If diamonds do form in the mantles of Uranus and Neptune, they would be denser than the surrounding material and would slowly sink toward the center of the planet. This process has been poetically described as diamond rain, a continuous precipitation of crystalline carbon falling through the hot, dense interior. Over the lifetime of the solar system, this diamond rain could have accumulated into a substantial layer around the rocky core, perhaps forming a shell of diamond thousands of miles thick. The idea of diamond rain is captivating, but it remains speculative. We have no way to directly observe the deep interiors of these planets, and laboratory experiments can only approximate the conditions found there. The actual behavior of matter at these extremes may be more complex than our models suggest. Nevertheless, the possibility of diamond rain illustrates the exotic nature of ice giant interiors, realms where familiar substances behave in unfamiliar ways. The transition from the icy mantle to the gaseous envelope above is gradual rather than abrupt. As one moves upward through the planet, pressure and temperature decrease, and the dense fluid of the mantle gradually becomes less dense until it merges with the atmosphere. There is no sharp boundary, no surface where one could stand. The planet simply becomes progressively less dense with altitude until the familiar atmosphere is reached. The gaseous envelope of hydrogen and helium extends from this transition zone up to the visible cloud tops. This envelope is relatively thin compared to the total radius of the planet, perhaps comprising only 10 to 20% of the planet's mass. The hydrogen in this envelope is molecular hydrogen, two hydrogen atoms bonded together, rather than the metallic hydrogen found in the deep interiors of Jupiter and Saturn. The absence of metallic hydrogen in the ice giants is significant for understanding their magnetic fields. In Jupiter and Saturn, the magnetic fields are thought to be generated by convection currents in the layer of metallic hydrogen, which conducts electricity like a metal. The ice giants lack this metallic hydrogen layer, so their magnetic fields must be generated elsewhere, probably in the conducting fluid of the icy mantle. The unusual configurations of the ice giant magnetic fields, tilted and offset from the planet's centers, may result from the geometry of the conducting region. If the magnetic field is generated in a relatively thin shell at intermediate depths, rather than in the central core, the field geometry would naturally be different from that of the gas giants. Computer simulations of magnetic field generation in ice giant interiors have reproduced some features of the observed fields, supporting this hypothesis. The internal heat budgets of Uranus and Neptune provide additional constraints on interior models. As discussed earlier, Neptune radiates about 2.6 times as much energy as it receives from the Sun, while Uranus radiates very little excess heat. This difference must be explained by any successful model of ice giant interiors. One possibility is that the interiors of the two planets have different degrees of compositional layering. If the interior is well mixed, with heavier materials distributed throughout, heat can flow relatively freely from the deep interior to the surface. But if the interior is stratified, with distinct layers of different composition, heat transport can be inhibited. A strongly stratified interior could trap heat in the deep regions, preventing it from reaching the surface. Some models suggest that Uranus has a more strongly stratified interior than Neptune, which would explain its lower heat output. The stratification might have been established by the giant impact that tilted Uranus on its side, which could have mixed the interior in a way that created stable compositional gradients. Neptune, which did not experience such an impact, might have a more well-mixed interior that allows heat to flow more freely. Another possibility involves the thermal evolution of the planets over the age of the solar system. Both planets formed hot, with substantial primordial heat from their gravitational contraction. Over billions of years, this heat has been gradually radiating away. If Uranus cooled more efficiently early in its history, perhaps due to the effects of the giant impact, it might have less residual heat to radiate today. The true explanation for the different heat outputs of Uranus and Neptune remains uncertain. This is one of the key questions that future missions to the ice giants could help answer. By measuring the gravitational fields, magnetic fields, and atmospheric compositions in greater detail, scientists could better constrain interior models and understand why these two similar planets behave so differently. The study of ice giant interiors has implications beyond our own solar system. Observations of exoplanets have revealed that planets intermediate in size between Earth and Neptune are extremely common in the galaxy. Many of these worlds may have compositions and structures similar to Uranus and Neptune, making the ice giants important analogues for understanding a common type of planet throughout the cosmos. Understanding the interiors of Uranus and Neptune could help us interpret observations of these distant worlds. The bulk density, atmospheric composition, and magnetic field of an exoplanet can provide clues about its interior structure, but interpreting these clues requires models validated against known examples. The ice giants of our own solar system provide the only accessible examples of this class of planet. As we conclude this journey into the deep interiors of the ice giants, let your imagination dwell on these hidden realms. Picture the crushing pressures, millions of times greater than Earth's atmosphere. Imagine the supersonic water, with its crystalline oxygen lattice and its flowing rivers of hydrogen. Envision the diamonds forming and falling, a slow rain of crystalline carbon sinking toward the heart of the planet over billions of years. These interiors are among the most extreme environments in the solar system, places where matter exists in forms unknown on Earth's surface. They remind us that the universe contains wonders beyond our everyday experience, phenomena that challenge our intuition and expand our understanding of what is possible. Uranus is accompanied through its long orbit by a retinue of moons, a collection of icy worlds that range from tiny irregular fragments to substantial spherical bodies with complex geologies. These moons share the planet's unusual orientation, orbiting in the plane of Uranus's tilted equator and thus experiencing the same extreme seasons as their parent world. The largest of these moons bear names drawn from the works of William Shakespeare and Alexander Pope, a literary tradition that sets the Uranian system apart from the mythological naming conventions used elsewhere in the solar system. The tradition of literary names began with the first two moons discovered, Titania and Oberon, found by William Herschel in 1787, just 6 years after his discovery of Uranus itself. Herschel named them after the fairy king and queen from Shakespeare's A Midsummer Night's Dream. When two more moons were discovered in 1851 by William Lassell, they received the names Ariel and Umbriel, characters from Alexander Pope's poem The Rape of the Lock. A fifth major moon, Miranda, discovered in 1948 by Gerard Kuiper, was named for the daughter of the magician Prospero in Shakespeare's The Tempest. These 5 moons, Miranda, Ariel, Umbriel, Titania and Oberon, are the major moons of Uranus, substantial worlds that were known before the space age and that have been studied in some detail. Beyond these 5, Voyager 2 discovered 10 additional small moons during its 1986 flyby, and subsequent observations from Earth have brought the total count to 28 known moons as of recent surveys. The smaller moons are named for other characters from Shakespeare's plays, maintaining the literary tradition. Let us begin our tour of the Uranian moons with the innermost and strangest of the major moons, Miranda. This small world, only about 290 miles in diameter, is one of the most geologically bizarre objects in the solar system. When Voyager 2 returned images of Miranda, scientists were astonished by what they saw. The surface displayed a chaotic jumble of terrains, unlike anything observed elsewhere. Miranda's surface is divided into distinct regions that seem almost randomly assembled. Vast tracts of ancient, heavily cratered terrain sit adjacent to younger regions marked by parallel grooves and ridges. 3 large features, called coronae, dominate portions of the surface. These corona are roughly oval regions bounded by concentric ridges and grooves with complex internal structures that suggest intense geological activity in the past. The most dramatic of Miranda's coronae is Verona Rupes, a cliff that rises approximately 12 miles from base to top, making it one of the tallest known cliffs in the solar system. If you stood at the base of Verona Rupes and looked up, the cliff face would stretch toward the sky at a dizzying angle, a wall of ice and rock reaching to heights that dwarf any terrestrial mountain. The origin of Miranda's chaotic surface has been debated since the Voyager encounter. One early hypothesis suggested that Miranda had been shattered by a massive impact and then reassembled from the fragments, with different pieces coming together in a haphazard arrangement. This dramatic scenario would explain the patchwork appearance of the surface. More recent analyses favour a different explanation involving internal geological processes. Miranda may have experienced episodes of tidal heating caused by gravitational interactions with Uranus and possibly other moons. This tidal heating could have warmed the interior, driving geological activity that reshaped portions of the surface. The coronae may be regions where warm, buoyant material rose from the interior, deforming the surface above. The intensity of past tidal heating on Miranda may have been greater than it is today. If the moon's orbit was once more eccentric, gravitational flexing would have been stronger, generating more internal heat. Over time, tidal interactions with Uranus would have circularized the orbit, reducing the heating and allowing the surface to freeze into its current configuration. Moving outward from Miranda, we encounter Ariel, the brightest and possibly the most geologically active of the major Uranian moons. Ariel has a diameter of about 720 miles and a surface that shows evidence of extensive resurfacing. The moon displays a network of valleys and fault scarps that crisscross the surface, along with smooth plains that appear to have been flooded by some kind of icy volcanic material. The valleys on Ariel are particularly striking. These features, called kasmata, can be dozens of miles wide and hundreds of miles long. They appear to have formed when the moon's icy crust was stretched and pulled apart, perhaps due to expansion of the interior as water froze. Some valleys have smooth floors that suggest they were later filled by eruptions of cryovolcanic material, icy slurries that flowed across the surface and solidified. The relatively few impact craters on Ariel's surface indicate that the moon has been geologically active in the relatively recent past, erasing older craters through resurfacing events. Among the major Uranian moons, Ariel appears to have the youngest surface, though the absolute age is difficult to determine without samples for radiometric dating. Umbriel presents a stark contrast to its neighbour Ariel. This moon, similar in size to Ariel at about 730 miles in diameter, has a dark, heavily cratered surface that shows little evidence of geological activity. Umbriel is the darkest of the major Uranian moons, reflecting only about 16% of the sunlight that strikes it. The surface appears ancient and battered, covered with impact craters accumulated over billions of years. The most distinctive feature on Umbriel is a bright ring on the floor of a crater named Wunda, located near the moon's equator. This bright deposit stands out against the otherwise uniformly dark surface. The nature of the bright material is unknown, but it may be relatively fresh ice exposed by the impact that formed the crater, or it may be material deposited from some internal source. The darkness of Umbriel's surface is thought to result from the accumulation of dark material over time, possibly carbon-rich compounds delivered by impacting objects, or produced by radiation processing of surface ices. The lack of geological activity means that this dark material has not been covered or removed, allowing it to accumulate and darken the surface over billions of years. Titania is the largest of the Uranian moons, with a diameter of about 980 miles. Like Ariel, Titania shows evidence of past geological activity, with a network of fault scarps and valleys crossing its surface. The moon appears to have experienced a period of global expansion early in its history, stretching the crust and creating the observed fault systems. The largest canyon on Titania, named Messina Chasmata, extends for nearly 1,000 miles across the surface. This enormous feature suggests that significant tectonic forces were at work, pulling the crust apart along this zone. The cause of the expansion may have been the freezing of water in the interior, which would have increased the moon's volume and stretched the outer crust. Titania's surface is moderately cratered, indicating an intermediate age between the heavily cratered Umbriel and the more recently resurfaced Ariel. Some craters show evidence of relaxation, their shape softened by the slow flow of ice over time. This relaxation suggests that the interior of Titania may have been warm enough at some point to allow the icy crust to deform gradually. Oberon, the outermost of the major moons, is similar in size to Titania at about 950 miles in diameter. Its surface is heavily cratered and ancient, resembling Umbriel more than the geologically active Ariel or Titania. However, Oberon does show some evidence of past activity, including a few large fault scarps and some craters with dark material on their floors. The dark material on the floors of some of Oberon's craters may be carbon-rich material that erupted from the interior, a form of cryovolcanism. Alternatively, it may be dark material excavated from beneath the surface by the impacts that form the craters. The presence of this dark material suggests that Oberon's interior may be differentiated, with layers of different composition. One of the most intriguing features on Oberon is a mountain that rises about 11 miles above the surrounding terrain, visible on the Moon's limb in Voyager images. This mountain may be the central peak of a large impact basin, thrust upward by the tremendous forces of the collision that formed it. Such towering peaks are rare in the solar system and speak to the violence of impacts in the early history of the moons. Beyond the 5 major moons, Uranus possesses numerous smaller satellites. The inner small moons, discovered by Voyager 2, orbit between Miranda and the planet, some of them embedded within or near the ring system. These moons are small, irregularly shaped bodies, probably fragments of larger objects that were broken apart by collisions. The outer irregular moons orbit at much greater distances from Uranus and have orbits that are often eccentric and inclined to the planet's equatorial plane. Many of these outer moons orbit in the retrograde direction, opposite to the planet's rotation. These characteristics suggest that the outer moons are captured objects, asteroids or comets, that wandered too close to Uranus and were snared by its gravity. The irregular moons are small and difficult to observe from Earth, so little is known about their physical properties. They are probably composed of ice and rock, similar to small bodies in the outer solar system. Their capture by Uranus would have required some mechanism to slow them down, perhaps drag from an extended atmosphere or disk of material that surrounded Uranus early in its history. The Uranian moon system as a whole presents a puzzle. The major moons orbit in nearly circular paths in the plane of Uranus's equator, suggesting that they formed from a disk of material surrounding the planet, similar to how the major moons of Jupiter and Saturn are thought to have formed. But Uranus's extreme axial tilt means that this disk would have been tilted as well, implying that the tilt was established before the moons formed. This timeline creates a problem. The giant impact thought to have tilted Uranus would have occurred early in solar system history, when the planet was still forming. But the impact would have generated enormous amounts of debris, and any pre-existing moons would likely have been destroyed or ejected. The current moons must have formed after the impact, from a disk of debris that was already tilted to match the planet's new orientation. Some models suggest that the impact itself created the disk from which the moons formed. The collision would have vaporized large amounts of ice and rock, which would have spread into a disk around the tilted planet and then coalesced into the moons we see today. This scenario explains why the moons orbit in the tilted equatorial plane, but it requires the impact to have been of just the right size and angle to produce the observed system. The moons of Uranus remain relatively poorly known compared to the moons of Jupiter and Saturn, which have been visited by multiple spacecraft over extended periods. Voyager 2's brief flyby in 1986 provided our only close-up views, and the geometry of the encounter limited observations of the northern hemispheres of the moons, which were in darkness at the time. Future missions to Uranus could reveal much more about these fascinating worlds. An orbiter could observe the moons over extended periods, mapping their entire surfaces and monitoring any changes. Closer flybys could reveal surface details invisible to Voyager. The moons of Uranus may harbour secrets as intriguing as those of the more famous moons of Jupiter and Saturn. As we prepare to leave the Uranian system and journey onward to Neptune, take a moment to picture these icy worlds circling their tilted parent planet. Miranda with its chaotic terrain and towering cliffs. Ariel with its valleys and smooth plains. Dark ancient Umbriel. Titania and Oberon, bearing the scars of billions of years of impacts and internal activity. These are worlds with stories to tell, stories that we have only begun to read. Neptune's system of moons is dominated by a single, extraordinary world, a moon so large and so strange that it overshadows all of its companions. This moon is Triton, and it is one of the most remarkable objects in the entire solar system. Triton is not merely interesting. It is a world that challenges our understanding of how moons form and evolve, a world with active geology despite the frigid temperatures of the outer solar system, a world that may offer clues to the nature of objects in the distant Kuiper belt. Triton was discovered in 1846, just 17 days after Neptune itself was found. The British astronomer William Lassell, using a telescope of his own construction, spotted the moon orbiting close to the newly discovered planet. For over a century, Triton remained a point of light, its true nature hidden by the vast distance separating it from Earth. The first hint that Triton was unusual came from observations of its orbit. Unlike most large moons in the solar system, Triton orbits Neptune in the retrograde direction, moving opposite to the planet's rotation. This retrograde orbit is highly unusual for a moon of Triton's size. Large moons typically form from disks of material surrounding their parent planets, and thus orbit in the same direction as the planet rotates. A retrograde orbit suggests a different origin. The explanation now widely accepted is that Triton did not form around Neptune at all. Instead, Triton is thought to be a captured object, a wanderer from the outer solar system that strayed too close to Neptune and was snared by the planet's gravity. Triton probably originated in the Kuiper belt, the vast region of icy bodies beyond Neptune's orbit. In this sense, Triton is a cousin of Pluto and other Kuiper belt objects, a representative of a population of distant, icy worlds that we are only beginning to explore. The capture of Triton would have been a violent event with far-reaching consequences. When Triton first entered Neptune's gravitational influence, it would have been on a highly elliptical orbit, swinging close to the planet and then retreating to great distances. Over time, tidal interactions with Neptune would have circularized the orbit, dissipating enormous amounts of energy in the process. This tidal heating would have dramatically affected Triton's interior, melting ice and driving geological activity. The heat generated during the capture and orbital circularization may have been sufficient to create a subsurface ocean of liquid water, which might persist to the present day. Triton may thus be another candidate for a habitable environment in the outer solar system, joining the ranks of Europa, Enceladus, and other icy moons with possible subsurface oceans. The capture of Triton would also have disrupted any pre-existing moon system around Neptune. The gravitational perturbations from the massive interloper would have destabilized the orbits of smaller moons, flinging some into Neptune, ejecting others into space, and leaving the system in chaos. The small moons that orbit Neptune today may be fragments of larger moons that were destroyed during this upheaval, or they may be objects captured later from the debris. Voyager 2's flyby of Neptune in August 1989 provided our only close look at Triton, and the images returned were astonishing. Triton revealed itself as a world of surprising complexity and activity, far more dynamic than anyone had expected for a moon in the frigid outer reaches of the solar system. The surface of Triton is young by geological standards, with very few impact craters. This paucity of craters indicates that the surface has been resurfaced relatively recently, erasing the record of ancient impacts. Something has been renewing Triton's face, covering old terrain with fresh material. The most likely explanation is cryovolcanism, the eruption of icy materials from the interior. On Triton, the erupted material is probably a mixture of water ice, nitrogen ice, and other frozen volatiles. This icy slurry would flow across the surface, filling in craters and creating smooth plains. The energy to drive this activity may come from residual tidal heating, radioactive decay in the interior, or some combination of sources. The surface of Triton displays a variety of terrains that speak to its complex geological history. The southern hemisphere, which was illuminated during the Voyager encounter, is covered by a bright polar cap of nitrogen and methane ice. This cap has a distinctive pinkish colour, probably due to complex organic compounds called tholins, which form when ultraviolet light and charged particles interact with nitrogen and methane. Beyond the polar cap, the surface shows regions of cantaloupe terrain, so named because its texture resembles the skin of a cantaloupe melon. This terrain consists of roughly circular depressions about 20 miles across, separated by ridges. The origin of cantaloupe terrain is debated, but it may result from a process called diaporism, in which blobs of warm, buoyant ice rise through the colder surface layers, creating the distinctive pattern. Voyager 2 made one of its most surprising discoveries when it observed active geysers on Triton's surface. Dark plumes of material were seen rising about 5 miles above the surface before being blown horizontally by winds in Triton's thin atmosphere, creating dark streaks on the bright polar cap. These geysers were completely unexpected on a world so cold and so far from the sun. The geysers of Triton are thought to be powered by solar heating, despite the feeble sunlight at Neptune's distance. The polar cap is composed of transparent nitrogen ice, which allows sunlight to penetrate to a depth of several feet. This sunlight warms darker material beneath the surface, vaporizing nitrogen and building up pressure until the gas erupts through weak points in the overlying ice. The process is somewhat analogous to the way sunlight can heat the interior of a greenhouse. The dark material carried aloft by the geysers settles back to the surface downwind, creating the dark streaks observed by Voyager. These streaks provide evidence of winds in Triton's thin atmosphere, which is composed primarily of nitrogen with traces of methane and carbon monoxide. The atmosphere is extremely tenuous, with a surface pressure about 70,000 times lower than Earth's atmospheric pressure. Triton's atmosphere is in a state of constant change, driven by the seasonal cycle of heating and cooling. As different parts of the surface are warmed by sunlight, nitrogen ice sublimates, adding gas to the atmosphere. When the surface cools, nitrogen condenses back onto the surface as frost. This cycle causes the atmosphere to migrate around the moon, thickening over warm regions and thinning over cold regions. The temperature on Triton's surface is about minus 391 degrees Fahrenheit, making it one of the coldest surfaces in the solar system. At these temperatures, nitrogen is a solid that behaves somewhat like water ice does on Earth, forming glaciers and ice caps that slowly flow and deform under their own weight. Methane and carbon monoxide are also frozen solid, contributing to the complex mixture of ices on the surface. Despite the extreme cold, Triton shows evidence of geological processes that continue to shape its surface. The cantaloupe terrain, the smooth plains, the polar cap with its geysers, all point to a world that is geologically alive. Triton is not a dead frozen relic, but an active world with ongoing processes that we are only beginning to understand. The size of Triton is impressive for a moon. With a diameter of about 680 miles, Triton is larger than Pluto and is the 7th largest moon in the solar system. Its density, about 2.06 grams per cubic centimetre, indicates a composition of roughly equal parts rock and ice, similar to Pluto and other large Kuiper Belt objects. The interior of Triton is probably differentiated, with a rocky core surrounded by an icy mantle. The core may be warm enough for liquid water to exist at the boundary between rock and ice, creating a subsurface ocean. This ocean, if it exists, would be a potential habitat for life, though conditions would be very different from Earth's oceans. The future of Triton is ultimately doom. Because of its retrograde orbit, tidal interactions with Neptune are causing Triton to spiral slowly inward. In perhaps 3.6 billion years, Triton will cross Neptune's Roche limit, the distance at which tidal forces exceed the Moon's own gravity. At that point, Triton will be torn apart, its material spreading into a ring around Neptune that might rival or exceed the rings of Saturn in grandeur. This fate lies far in the future, but it reminds us that the solar system is not static. The configurations we see today are snapshots in an ongoing process of change. Moons are captured, orbits evolve, worlds are destroyed and created. The solar system is a dynamic place, even if the changes occur on timescales far longer than human lives. Beyond Triton, Neptune possesses 15 other known moons, though none approach Triton in size or interest. The largest of these smaller moons is Proteus, an irregularly shaped body about 260 miles across. Proteus orbits closer to Neptune than Triton and was discovered by Voyager 2. It is dark and heavily cratered, a battered remnant that may be a fragment of a larger moon destroyed during Triton's capture. Nereid, discovered in 1949, has the most eccentric orbit of any moon in the solar system. Its distance from Neptune varies from about 841,000 miles to about 5.9 million miles, a range that takes it from relatively close to the planet to far out into space. This extreme eccentricity suggests that Nereid's orbit was severely disturbed by some past event, probably the capture of Triton. The other small moons of Neptune are mostly tiny, irregularly shaped bodies discovered by Voyager 2 or by ground-based observations in subsequent years. Some of these moons orbit within or near Neptune's ring system and may serve as sources of ring material. Others orbit at great distances and may be captured objects from the Kuiper Belt. The moon system of Neptune, shaped by the dramatic capture of Triton, is fundamentally different from the moon systems of the other giant planets. Jupiter, Saturn, and Uranus all possess families of regular moons that formed in place from circumplanetary disks. Neptune's regular moons, if they ever existed, were destroyed or ejected when Triton arrived. What remains is a system dominated by a captured interloper, with only small fragments and captured strays to keep it company. As we conclude our exploration of Neptune's moons, let your mind dwell on the image of Triton, that pink and white world with its geysers and its cantaloupe terrain. Here is a moon that was born elsewhere in the cold darkness beyond the planets and was captured by Neptune to become part of our planetary system. Triton carries secrets about the Kuiper Belt, about the early solar system, about the processes that shape icy worlds far from the sun. When we think of planetary rings, the magnificent system of Saturn inevitably comes to mind. Those broad, bright bands of ice have captivated observers since Galileo first glimpsed them through his primitive telescope in 1610. But Saturn is not alone in possessing rings. All 4 giant planets of our solar system are encircled by ring systems, though the rings of Jupiter, Uranus, and Neptune are far more subtle than Saturn's glorious display. The rings of Uranus were discovered on March 10, 1977, through a fortunate combination of careful planning and serendipitous timing. A team of astronomers led by James Elliott was observing Uranus as it passed in front of a distant star, an event called a stellar occultation. The primary goal was to study Uranus's atmosphere by analysing how it affected the star's light as the planet passed in front of it. But before Uranus itself blocked the star, the astronomers noticed something unexpected. The star's light flickered briefly, dimming and then brightening again. This flickering occurred several times, in a symmetric pattern on both sides of the planet. Something was blocking the starlight before and after the planet itself passed in front of the star. That something was a system of rings. The discovery was a surprise. Astronomers had searched for rings around Uranus before without success, and the prevailing view was that only Saturn possessed a significant ring system. The rings of Uranus had escaped detection because they are extremely dark, reflecting only a few % of the sunlight that strikes them. They are also narrow, thin bands rather than broad sheets, making them even harder to spot. Subsequent observations revealed the extent of the Uranian ring system. 9 distinct rings were identified from Earth-based observations, and Voyager 2 discovered 2 additional faint rings during its 1986 flyby. The rings are designated by letters and numbers, with the brightest and most prominent ring called the Epsilon ring. The Epsilon ring is the outermost of the main rings, orbiting about 32,000 miles from the centre of Uranus. Despite being the most prominent ring, it is remarkably narrow, varying in width from about 12 miles to about 60 miles. The ring is also eccentric, meaning its distance from Uranus varies as it goes around the planet. This eccentricity causes the ring to be wider at its most distant point from the planet and narrower at its closest approach. The narrowness of the Epsilon ring presents a puzzle. Left to themselves, ring particles would spread out over time due to collisions and gravitational interactions. A narrow ring should broaden and diffuse unless something confines it. The answer to this puzzle came with the discovery of 2 small moons, Cordelia and Ophelia, orbiting on either side of the Epsilon ring. These moons act as shepherds, their gravity herding the ring particles and preventing them from spreading. Cordelia orbits just inside the ring, while Ophelia orbits just outside. Particles that drift inward are pushed back out by gravitational interactions with Cordelia, while particles that drift outward are pushed back in by Ophelia. This gravitational shepherding maintains the ring's narrow width against the natural tendency to spread. The concept of shepherd moons was predicted theoretically before the Uranian rings were discovered, but Uranus provided the first clear example of this phenomenon in action. Shepherd moons have since been identified in the ring systems of other planets, including Saturn, where small moons confine some of the narrower rings. The composition of the Uranian rings is not entirely certain, but they appear to be composed of water ice mixed with dark organic material. The darkness of the rings, which reflect only about 5% of incident light, suggests that the ice is heavily contaminated with carbon-rich compounds. These compounds may have been produced by radiation processing of methane and other hydrocarbons, or they may have been delivered by impacting objects. The particles in the Uranian rings range in size from tiny dust grains to boulders several feet across. The size distribution affects how the rings scatter light and how they respond to gravitational perturbations. Observations at different wavelengths have helped constrain the particle sizes, but much remains uncertain. The age of the Uranian rings is a subject of debate. Some scientists believe the rings are ancient, dating back to the particles in the Uranian rings range in size from tiny dust grains to boulders several feet across. Voyager 2's observations revealed that the main rings consist mostly of large particles, objects greater than about 4.6 feet across, while microscopic dust particles in the micrometer size range were found distributed in the spaces between the main rings rather than within them. This distribution suggests that the rings are losing mass as a result of collisions, with dust being generated and then migrating away from the main ring structures. The size distribution affects how the rings scatter light and how they respond to gravitational perturbations. Observations at different wavelengths have helped constrain the particle sizes, but much remains uncertain. The age of the Uranian rings is a subject of debate. Some scientists believe the rings are ancient, dating back to the early history of the solar system, while others argue that they are relatively young, perhaps only a few 100 million years old. The youth hypothesis is supported by the observation that ring systems naturally spread and dissipate over time. Without some mechanism to replenish them, ancient rings would have long since dispersed. One possible source of replenishment is the destruction of small moons. Impacts from comets or asteroids could shatter moons orbiting within or near the ring zone, creating fresh ring material. The small moons discovered by Voyager 2 in the Uranian system may be remnants of larger bodies that were partially destroyed, with the debris forming the rings we see today. Another possibility is that the rings are continuously fed by material from the moons themselves. Micrometeorite impacts on the surfaces of small moons would eject particles into orbit, gradually adding to the ring mass. This process could maintain the rings over long periods, even if individual ring particles have relatively short lifetimes. The interaction between the rings and Uranus's atmosphere is another area of active research. Tiny dust particles from the rings fall onto Uranus due to the planet's gravity and forces in its atmosphere. These particles come from the rings and collide with gases in the upper atmosphere, gradually making their way down toward deeper levels. When dust particles move through Uranus's atmosphere, they experience drag, which affects their speed and direction. This process helps scientists understand where the dust comes from and how it behaves as it falls toward the planet. The rings of Uranus are tilted along with the planet itself, sharing the extreme 98-degree axial tilt that makes Uranus unique among the planets. This means that the rings are sometimes seen nearly face-on from Earth and sometimes seen edge-on, depending on where Uranus is in its 84-year orbit. The edge-on viewing geometry, called a ring plane crossing, occurred in 2007 and provided valuable opportunities for observation. During ring plane crossings, the rings become very difficult to see because we are looking at them from the side, but faint features that are normally overwhelmed by the brighter main rings can become visible. The 2007 ring plane crossing allowed astronomers to study the dust bands and faint outer rings in detail, revealing changes since the Voyager encounter 2 decades earlier. The rings of Neptune were suspected before Voyager 2's arrival, but remained controversial. Ground-based stellar occultation observations in the 1980s detected brief dips in starlight that suggested the presence of rings, but the results were inconsistent. Some observations detected material, while others did not, leading to the puzzling suggestion that Neptune might have incomplete ring arcs rather than full rings. Voyager 2 resolved this mystery when it flew past Neptune in August 1989. The spacecraft revealed that Neptune does indeed possess a complete ring system, but the rings are extremely faint and contain regions of enhanced density that create the appearance of arcs when viewed from Earth. The rings are so tenuous that they were invisible in most Voyager images and could only be detected in long-exposure photographs taken when the spacecraft was positioned to see sunlight scattered forward through the rings. Neptune's ring system consists of 5 main rings, named after scientists who contributed to the study of Neptune. From innermost to outermost, these are the Gale ring, the Leverrier ring, the Lassell ring, the Arago ring, and the Adams ring. The Adams ring, the outermost and most prominent, contains the ring arcs that had puzzled ground-based observers. The ring arcs in the Adams ring were given names honouring the French Revolution: Liberté, Égalité, and Fraternité, along with two smaller arcs called Courage and Fraternité. These arcs are regions where ring material is concentrated, creating bright spots along the otherwise faint ring. The arcs span only a fraction of the ring's circumference, with large gaps of sparse material between them. The existence of ring arcs poses a theoretical problem. Ring particles naturally spread out along their orbits due to collisions and gravitational interactions. An arc should disperse into a uniform ring within a relatively short time, perhaps a few years to a few decades. Yet the arcs observed by Voyager 2 appeared stable, suggesting that some mechanism was confining them. The leading explanation involves gravitational resonances with Neptune's small moon Galatea, which orbits just inside the Adams ring. Galatea's gravity creates a pattern of gravitational perturbations that can trap ring particles at certain locations, preventing them from spreading. This resonance confinement is similar to the shepherd moon mechanism that maintains the narrow rings of Uranus, but it operates through a different dynamical process. However, observations of Neptune's rings since the Voyager encounter have revealed that the arcs are not as stable as initially thought. Hubble space. Telescope and ground-based observations in the 1990s and 2000s showed that the arcs have changed significantly since 1989. Some arcs have faded while others have brightened, and the overall distribution of material has shifted. The arcs appear to be evolving on timescales of decades, much faster than the resonance confinement theory predicted. This evolution suggests that our understanding of the arc confinement mechanism is incomplete. Perhaps additional factors, such as collisions between ring particles or interactions with dust, play a role in the arc's behaviour. Or perhaps the arcs are not truly stable structures, but transient features that form and dissipate over time. The limited observations available make it difficult to distinguish between these possibilities. The composition of Neptune's rings is similar to that of Uranus's rings. The particles are dark, reflecting only a few % of incident sunlight, and are probably composed of water ice mixed with dark organic compounds. The darkness of the rings explains why they were so difficult to detect from Earth, and why they appear so faint even in Voyager images. The particle sizes in Neptune's rings span a wide range, from microscopic dust to larger chunks. The dust component is particularly prominent in Neptune's rings, giving them a somewhat different character from the rockier rings of Uranus. This dust may be continuously generated by collisions between larger particles and by micrometeorite impacts on small moons embedded in the ring system. The innermost ring of Neptune, the Gal ring, is broad and diffuse, extending over a width of about 200 miles. This ring is extremely faint and was only detected in Voyager's forward scattered light images. The Leverrier ring farther out is narrower and somewhat brighter. Between the Leverrier and Adams rings lies the Lassell ring, another broad and faint structure, with a narrow Arago ring embedded within it. The total mass of Neptune's ring system is tiny, probably less than the mass of a small moon a few miles across. The rings are so tenuous that, if all the material were gathered together, it would form only a modest pile of dark icy rubble. Yet this sparse material, spread across thousands of miles of space, creates structures that can be detected across billions of miles. The rings of both ice giants share several characteristics that distinguish them from Saturn's famous rings. Both are dark, composed of material that absorbs most of the light that strikes it. Both are narrow, consisting of thin bands rather than broad sheets. Both are faint, requiring careful observation to detect. And both are dynamic, showing evidence of ongoing evolution and change. These characteristics may reflect the different histories and environments of the ice giant ring systems compared to Saturn's rings. Saturn's rings are thought to be relatively young, perhaps formed by the destruction of a large moon within the last few 100 million years. The bright, icy composition of Saturn's rings suggests that they have not had time to accumulate the dark coating of organic material that darkens the rings of Uranus and Neptune. Alternatively, the ice giant rings may be continuously replenished by different processes than Saturn's rings, leading to different compositions and structures. The smaller sizes of Uranus and Neptune compared to Saturn mean weaker tidal forces, which could affect how ring material is generated and distributed. The different populations of small moons in each system could also lead to different ring characteristics. The study of planetary rings has revealed that these structures are far more complex and dynamic than early observers imagined. Rings are not static features but evolving systems shaped by gravity, collisions, and interactions with moons. They provide natural laboratories for studying the physics of disk systems, with applications ranging from understanding the early solar nebula to interpreting observations of disks around other stars. As we conclude our exploration of the rings of Uranus and Neptune, take a moment to picture these dark, narrow structures encircling their distant parent planets. Unlike Saturn's brilliant rings, which blaze with the reflected sunlight, the rings of the ice giants are subtle and secretive, revealing themselves only to patient observers with sensitive instruments. They are rings of darkness, hidden halos that remind us how much remains to be discovered in the outer reaches of our solar system. Let your breathing slow and your body relax as we prepare to journey back in time to humanity's only close encounter with these distant worlds. In the summer of 1977, 2 spacecraft lifted off from Cape Canaveral, Florida, beginning journeys that would transform our understanding of the outer solar system. Voyager 1 and Voyager 2 were designed to take advantage of a rare alignment of the giant planets, a configuration that occurs only once every 175 years. This alignment would allow a single spacecraft to visit multiple planets, using the gravity of each world to bend its trajectory toward the next. Voyager 1 was targeted for close encounters with Jupiter and Saturn, with a trajectory that would take it out of the plane of the solar system after its Saturn flyby. Voyager 2 followed a different path, one that would carry it past all 4 giant planets: Jupiter, Saturn, Uranus, and Neptune. This grand tour trajectory made Voyager 2 the only spacecraft ever to visit the ice giants, a distinction it holds to this day. The Voyager spacecraft were marvels of 1970s engineering, designed to operate for years in the harsh environment of deep space. Each spacecraft carried a suite of scientific instruments capable of studying planetary atmospheres, magnetic fields, moons, and rings. Cameras could capture images in visible light and other wavelengths. Spectrometers could analyze the composition of atmospheres and surfaces. Magnetometers could measure magnetic fields. Radio science experiments could probe planetary interiors and atmospheres. The spacecraft were powered by radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium into electricity. Unlike solar panels, which become useless far from the sun, these nuclear power sources could operate for decades, providing the energy needed to run instruments and transmit data back to Earth. Communication with the Voyager spacecraft required the Deep Space Network, a system of large radio antennas located in California, Spain, and Australia. As the spacecraft travelled farther from Earth, the radio signals became weaker and weaker, requiring ever more sensitive receivers to detect them. By the time Voyager 2 reached Neptune, its radio signal had a power of about 20 watts, similar to a refrigerator light bulb spread across billions of miles of space. Voyager 2 encountered Jupiter in July 1979, returning stunning images of the giant planet's turbulent atmosphere and its 4 large moons. The spacecraft discovered volcanic eruptions on Io, the innermost of the Galilean moons, and found evidence for a subsurface ocean on Europa. These discoveries revolutionized our understanding of the Jovian system and whetted appetites for what lay ahead. Saturn came next, in August 1981. Voyager 2 complemented the observations made by Voyager 1 9 months earlier, providing additional views of the ringed planet and its moons. The spacecraft flew close to Enceladus, revealing a surface of fresh ice that hinted at geological activity. It also studied Titan, Saturn's largest moon, though the thick atmosphere prevented direct views of the surface. After Saturn, Voyager 2 began the long cruise to Uranus, a journey of more than 4 years across billions of miles of empty space. During this time, engineers on Earth worked to prepare the spacecraft for the challenges ahead. The faint light at Uranus would require longer camera exposures, which in turn required more precise pointing to avoid blurring. Software updates were transmitted to the spacecraft, upgrading its capabilities for the encounters to come. Voyager 2 arrived at Uranus on January 24, 1986, passing within about 50,600 miles of the planet's cloud tops. The encounter was brief, lasting only a few hours at closest approach, but the data returned transformed our understanding of this distant world. The images of Uranus revealed a planet that appeared remarkably bland compared to Jupiter and Saturn. The blue-green disk showed few visible features, with none of the colourful bands and swirling storms that characterised the larger gas giants. Scientists had hoped to see atmospheric activity driven by Uranus's extreme seasons, but the planet presented a nearly featureless face. This apparent blandness was partly due to the viewing geometry. At the time of the Voyager encounter, Uranus's south pole was pointing almost directly at the Sun, and the spacecraft approached from this direction. The entire southern hemisphere was in continuous daylight, while the northern hemisphere was hidden in darkness. Any atmospheric features in the north were invisible to Voyager's cameras. Despite the bland appearance, Voyager's instruments detected significant atmospheric activity. The spacecraft measured wind speeds of several hundred miles per hour, with the winds blowing in the retrograde direction at the equator. Temperature measurements revealed that the poles and equator had similar temperatures, despite the extreme differences in solar heating, suggesting efficient heat transport within the atmosphere. The magnetic field of Uranus proved to be one of the encounter's biggest surprises. Scientists had expected a magnetic field roughly aligned with the planet's rotation axis, similar to the fields of Earth, Jupiter, and Saturn. Instead, Voyager found a field tilted 59 degrees from the rotation axis and offset from the planet's centre by about 1/3 of the planet's radius. This bizarre configuration suggested that Uranus's magnetic field was generated in a fundamentally different way from the fields of other planets. Voyager 2 discovered 10 new moons of Uranus, all small and irregularly shaped, orbiting close to the planet, within or near the ring system. These moons, along with the 2 shepherd moons Cordelia and Ophelia, brought the total count of known Uranian moons to 15 at the time. The spacecraft also provided the first detailed views of the 5 major moons: Miranda, Ariel, Umbriel, Titania, and Oberon. Each moon revealed its own unique character. Miranda's chaotic surface, with its coronae and towering cliffs, was the most surprising. Ariel showed evidence of geological activity, while Umbriel appeared dark and ancient. Titania and Oberon displayed fault systems and impact craters that spoke to their long histories. The rings of Uranus, discovered 9 years earlier through stellar occultation, were imaged directly for the first time. Voyager revealed the narrow, dark rings in detail, along with faint dust bands between the main rings. The spacecraft confirmed the existence of the shepherd moons that confine the Epsilon ring and discovered additional ring structure invisible from Earth. After the Uranus encounter, Voyager 2 continued outward toward its final planetary destination. The cruise to Neptune took another 3.5 years, during which engineers continued to refine the spacecraft's capabilities. The challenges at Neptune would be even greater than at Uranus. The planet was farther from the Sun, meaning even less light for imaging. The distance from Earth was greater, meaning weaker radio signals and longer communication delays. Voyager 2 arrived at Neptune on August 25, 1989, 12 years after leaving Earth. The spacecraft passed within about 3,000 miles of Neptune's cloud tops, the closest approach of any Voyager planetary encounter. This close passage was deliberate, designed to bend Voyager's trajectory toward Triton for a close flyby of that intriguing moon. Neptune proved to be far more visually interesting than Uranus. The deep blue planet displayed distinct atmospheric features, including the Great Dark Spot, a massive storm system comparable in size to Earth. Bright white clouds of methane ice cast shadows on the deeper atmosphere, and bands of different colours indicated variations in atmospheric composition or cloud altitude. The winds of Neptune were measured at nearly sun 200 miles per hour, the fastest in the solar system. This was surprising given Neptune's great distance from the Sun and the feeble solar heating it receives. The energy driving these winds must come primarily from Neptune's internal heat, which the planet radiates at about 2.6 times the rate it receives from the Sun. Neptune's magnetic field proved to be as strange as that of Uranus, tilted 47 degrees from the rotation axis and offset from the planet's centre. The similarity between the magnetic fields of the two ice giants suggested that their unusual configurations might be a common feature of this class of planet, perhaps related to their internal structures. Voyager 2 discovered 6 new moons of Neptune, all small bodies orbiting close to the planet. The spacecraft also revealed the structure of Neptune's ring system, confirming the existence of complete rings and explaining the ring arcs that had puzzled ground-based observers. The arcs were shown to be regions of enhanced density within the Adam's ring, confined by gravitational resonances with the moon Galatea. The highlight of the Neptune encounter was the close flyby of Triton. Voyager passed within about 25,000 miles of the moon's surface, returning images that revealed a world of astonishing complexity. The cantaloupe terrain, the nitrogen polar cap, the active geysers, all were discovered during this brief encounter. Triton emerged as one of the most fascinating objects in the solar system, a world that demanded further exploration. After the Neptune encounter, Voyager 2 continued outward into the darkness, following Voyager 1 toward interstellar space. Both spacecraft are still operating today, more than 4 decades after their launch, returning data about the outer heliosphere and the boundary between the Sun's influence and the interstellar medium. Voyager 1 crossed into interstellar space in 2012, and Voyager 2 followed in 2018. They are the most distant human-made objects, ambassadors from Earth travelling among the stars. The legacy of the Voyager missions is difficult to overstate. Before Voyager, the outer planets were distant points of light, known only through telescopic observations. After Voyager, they were real worlds, places with weather and geology and moons and rings. The images returned by Voyager have become iconic, shaping how generations of people visualize the solar system. For Uranus and Neptune specifically, Voyager 2 remains our only source of close-up data. Everything we know about the detailed appearance of these planets, their moons, their rings, and their magnetic fields comes from those brief encounters in 1986 and 1989. The spacecraft spent only hours at closest approach to each planet, gathering data as quickly as possible before continuing on its journey. This limited data set leaves many questions unanswered. We have seen only portions of the surfaces of the major moons, with large areas remaining unmapped. We have observed the atmospheres at single points in time, unable to track how they change over seasons or years. We have measured the magnetic fields along single trajectories, unable to fully characterize their complex geometries. The scientific community has long recognized the need to return to the ice giants with modern spacecraft and instruments. The technology available today far surpasses what was possible in the 1970s when Voyager was designed. Modern cameras could capture images with far greater resolution and sensitivity. Modern spectrometers could analyze atmospheric and surface compositions in much greater detail. An orbiter could study the planets over extended periods, observing seasonal changes and tracking the evolution of atmospheric features. More than 3 decades have passed since Voyager 2 flew past Neptune, completing its grand tour of the outer solar system. In that time, spacecraft have returned to Jupiter and Saturn multiple times. The Galileo orbiter spent 8 years studying Jupiter and its moons. The Cassini mission orbited Saturn for 13 years, revolutionizing our understanding of the ringed planet and its remarkable moon Titan. The Juno spacecraft currently orbits Jupiter, probing the giant planet's deep atmosphere and interior. But Uranus and Neptune have received no visitors since Voyager. The ice giants remain the least explored planets in our solar system, known primarily through that single brief encounter and through observations made from Earth and Earth-orbiting telescopes. This situation is widely recognized as a gap in our exploration of the solar system, and the scientific community has repeatedly called for new missions to these distant worlds. The case for returning to the ice giants is compelling. Uranus and Neptune represent a class of planet that is common in the galaxy, but poorly understood. Observations of exoplanets have revealed that planets intermediate in size between Earth and Neptune are among the most abundant types of planets orbiting other stars. Understanding our own ice giants is essential for interpreting observations of these distant worlds and for understanding planetary formation and evolution in general. The questions left unanswered by Voyager are numerous and significant. What is the internal structure of the ice giants, and why do Uranus and Neptune have such different heat outputs despite their similar sizes? What drives the extreme winds on Neptune, and why is Uranus's atmosphere so much calmer? What is the nature of the unusual magnetic fields, and what do they tell us about the planet's interiors? How do the atmospheres change over seasonal timescales? What is the composition of the deep atmospheres below the levels that can be observed from Earth? The moons of the ice giants also demand further study. Miranda's chaotic surface hints at a complex geological history that we barely understand. Triton's active geysers and young surface suggest ongoing processes that could be studied in detail by an orbiter. The possibility of subsurface oceans on some of these moons raises questions about habitability in the outer solar system. The rings of Uranus and Neptune, dynamic and evolving, could be studied over time to understand the processes that shape them. The small moons embedded in and near the rings could be characterized in detail, revealing their compositions and origins. In 2022, the United States National Academies of Sciences, Engineering, and Medicine released its Planetary Science and Astrobiology Decadal Survey, a report that sets priorities for planetary exploration over the coming decade. The survey identified a Uranus orbiter and probe as the highest priority new flagship mission for NASA to pursue. This recommendation reflected the scientific community's consensus that the ice giants have been neglected for too long and that a dedicated mission is needed to address fundamental questions about these worlds. The recommended mission concept would send a spacecraft to orbit Uranus for several years, studying the planet, its moons, and its rings in detail. An atmospheric probe would be released to descend into Uranus's atmosphere, directly measuring composition, temperature, pressure, and wind speeds at different depths. This combination of orbiter and probe would provide a comprehensive picture of the Uranian system far beyond what Voyager could achieve in its brief flyby. The journey to Uranus would take about 13 years using current propulsion technology, assuming a gravity assist from Jupiter along the way. This long travel time is one of the challenges of outer solar system exploration. Missions must be designed to operate for decades, from launch through cruise to arrival, and then through years of orbital operations. The scientists who propose such missions may not live to see them completed. The cost of a flagship mission to Uranus would be substantial, likely several $billion spread over many years. Such missions compete for funding with other scientific priorities, and budget constraints have repeatedly delayed plans for ice giant exploration. Nevertheless, the 2022 Decadal Survey's strong endorsement has raised hopes that a Uranus mission might finally move forward. Neptune, though not selected as the top priority, also remains a target of scientific interest. A Neptune mission would face even greater challenges than a Uranus mission due to the planet's greater distance. The travel time would be longer, the communication delays greater, and the available power from radioisotope generators lower due to the decay of the plutonium fuel over the extended cruise. However, Neptune offers unique scientific opportunities that Uranus cannot provide. Triton, with its active geology and possible subsurface ocean, is one of the most compelling targets in the outer solar system. A mission to Neptune could study Triton in detail, perhaps even landing on its surface to analyze the composition of its ices and search for signs of geological activity. Some mission concepts have proposed visiting both ice giants on a single grand tour, similar to Voyager's trajectory, but with modern instruments and the ability to enter orbit rather than simply flying past. Such a mission would be extraordinarily ambitious and expensive, but it would maximize the scientific return from the long journey to the outer solar system. International cooperation could help make ice giant missions more feasible. The European Space Agency, the Japanese Aerospace Exploration Agency, and other space agencies have expressed interest in participating in missions to Uranus or Neptune. Sharing the costs and responsibilities of such missions could make them more achievable than any single nation could accomplish alone. Technology development is also advancing the prospects for ice giant exploration. New propulsion systems, such as solar electric propulsion, could reduce travel times or increase the mass of scientific instruments that can be delivered. Advances in autonomous navigation and operations could allow spacecraft to function more independently, reducing the burden on ground controllers during the long cruise phase. Smaller, less expensive missions have also been proposed as complements to flagship missions. A flyby mission, similar to New Horizons' encounter with Pluto, could reach Uranus or Neptune more quickly and at lower cost than an orbiter. While a flyby would provide less data than an orbiter, it could answer some key questions and build momentum for more ambitious follow-up missions. The scientific instruments that would fly on future ice giant missions would far surpass Voyager's capabilities. Modern cameras could capture images with resolution measured in feet rather than miles. Spectrometers could identify specific minerals and ices on moon surfaces. Radar could penetrate clouds and even probe beneath the surfaces of moons. Magnetometers and plasma instruments could characterize the magnetic environments in unprecedented detail. An atmospheric probe descending into Uranus or Neptune would provide data impossible to obtain any other way. By directly sampling the atmosphere at different depths, a probe could measure the abundances of key elements and isotopes that constrain models of planetary formation. The probe could measure wind speeds and directions, revealing the three-dimensional structure of atmospheric circulation. It could detect clouds and hazes, determining their compositions and altitudes. The probe would face extreme challenges during its descent. The atmosphere would slow it from interplanetary speeds, generating intense heat that must be absorbed by a heat shield. As it descended deeper, pressure and temperature would rise, eventually crushing and melting the probe. The goal would be to transmit data for as long as possible before the probe succumbed to the hostile environment. Similar probes have been sent to Venus, Jupiter and Titan, demonstrating that the technology exists to survive atmospheric entry and return valuable data. A probe at Uranus or Neptune would face conditions different from these previous missions, but within the range of current engineering capabilities. The timeline for ice giant exploration remains uncertain. Even with strong scientific endorsement, missions take decades to move from concept to launch. A Uranus orbiter and probe, if approved in the near future, might not launch until the late 2030s and would not arrive until the 2050s. Scientists and engineers must think in terms of generations, planning missions that their successors will execute and whose results their successors' will analyse. This long timescale can be discouraging, but it also reflects the grandeur of the endeavour. Exploring the outer solar system is not a task for the impatient. It requires sustained commitment across decades, the willingness to invest in projects whose benefits lie far in the future. The scientists who first proposed missions to Uranus and Neptune in the 1980s and 1990s are now retired or deceased, but their vision may finally be realised by a new generation. The ice giants wait in the darkness, patient and unchanging on human timescales. Uranus continues its slow roll around the Sun, its tilted axis carrying it through seasons that last longer than human lifetimes. Neptune's winds howl at supersonic speeds, storms forming and dissipating unseen by human eyes. Triton's geysers erupt into the thin atmosphere, depositing dark streaks on the nitrogen ice. The moons of Uranus circle their tilted parent, their surfaces bearing the scars of ancient impacts and geological upheavals. These worlds have stories to tell, secrets to reveal, wonders to display. They have waited billions of years for someone to come and look. They can wait a few decades more. The exploration of the ice giants is not merely a scientific endeavour. It is an expression of human curiosity, a reaching out toward the unknown, a refusal to accept that some things are simply too far away to understand. The ice giants challenge us to extend our reach, to develop new technologies, to commit resources across generations. Meeting that challenge would say something important about who we are as a species. Let your body relax completely as we prepare to bring our journey to a close. In our final moments together, we will reflect on what we have learned and what these distant worlds mean for our understanding of the cosmos and our place within it.